Consider two concentric circles. If half the tangent chord is A, and the circles have radii little r and big R, then we can use the Pythagorean theorem and solve for a squared. We also see the annular area is the area of the larger circle minus the area of the smaller one. But the difference of squares was just a squared. This means the individual radii don't actually matter, only the length of A. We can see this even when A equals 0. What if there was a way to see this intuitively? If we draw the tangent line A and sweep it around the inner circle, and bring the points of tangency together to a common point O, a circle with radius A is formed. And we get the same result of pi times A squared. This finding is also true for an ellipse where we draw a tangent with length L. Once again, if we sweep this tangent line around the ellipse and translate each resulting tangent so that the point of tangency is brought to a common point O, the area swept out is a circular disk with radius L and area equal to pi times the length of the tangent line squared. In fact, this is true for any closed convex curve. For example, in the case of this superellipse, we again find the same result. The actual shape doesn't matter, only the length L of the tangent line. Or this limison. This means that because the area doesn't matter, and a disk is always formed for any such convex curve, we can essentially just imagine rotating all the tangents around the center of a circle. The method known as visual calculus was first found by Armenian undergraduate Mamikon Mnatsakanian, and was later further developed with himself and Apostol at Caltech. This theorem for oval rings states that all oval rings swept by a tangent of given length have equal areas, regardless of their shape. Now let's look at a few other use cases of visual calculus. We can use it to find the area under a tractrix. Imagine a child walking along a straight path. As the child walks, his toy is dragged along, tracing out a curve called the tractrix. Finding the area underneath is difficult with traditional calculus. However, using visual calculus, because the line between each point on the graph and the child's position is tangent to the curve, and the child continues to infinity, we can easily see the area approaches a quarter circle, where the radius is the length of the child's string. Visual calculus also helps us find the cycloid area. As the circle rolls, point T traces the cycloid, while point Q remains at the top. The tangents are drawn between T and Q. This time, we get a full circle of radius r. The bounding rectangle has width of the circle's circumference and height of its diameter. From the rectangle's total area, we subtract the shaded area to find the cycloid area is 3 times the circle's. But the real beauty of visual calculus comes when we don't know the equations of our curves. Consider the paths of bicycle wheels. The area between them has positive and negative contributions. The negative areas and the positive areas cancel out, leaving a partial circle. The remaining sector is based on the change in direction of the bicycle frame. In fact, The tractrix from earlier is actually a special case of this bicyclics, where, instead of a child, the front wheel travels along the x-axis, and the bicycle goes through an angle of 90 degrees. Visual calculus, therefore, is a powerful tool allowing us to approach calculus through geometric intuition. It's this kind of differential thinking that leads us to discovery.